Hello, good day. My name is Satishilan and today I'll be presenting my undergraduate project entitled The Effect of Pad Modification on Brake Squeal Occurrences. Without further ado, let's get started. Hello again. As I mentioned earlier, this is my undergraduate project titled The Effect of Pad Modification on Brake Squeal Occurrences, presented by myself, Satishilan Amamuthu, Supervisor Dr. Abdurrahim bin Abu Bakar. Presentation outline consists of introduction, literature review, research approach, methodology, result and discussion, conclusion, recommendation, and references. In UGP1, I've already presented from introduction till methodology. For this presentation, I'll be focusing more on result and discussion till references. Starting from introduction, as you can see at the picture, it shows type of brake noises, frequency range for brake noise and vibration issues. Our focus are mainly from 1 kHz till 15 kHz, which is low frequency squeal, till high frequency squeal. Squeal noise happen due to friction induced vibration or self-excited vibration via a rotating disc or rotor. It occurs at frequency above 1 kHz and is described as sound pressure level above 70 dBA. Squeal noise challenges car makers, brake and friction material suppliers for high warranty claim. It also irritates and disturbance to people and environment. Problem statement: car makers and brake suppliers use pad shim that sticks to the backplate to eliminate brake squeal. Inserting the pad shim can add extra production and assembly costs. Structural modification including pad modification can be another potential solution to reduce or eliminate squeal. This undergraduate project is intended to investigate whether brake pad modification through slots and camphor can effectively eliminate or reduce brake squeal noise. The aim of this project is to reduce the squeal noise below 70 dBA by modifying the pad geometry, focusing on mainly camphor and slot. Research objective to study the effect of pad modification and brake squeal occurrences. My scope: front brake assembly to be tested in Persona car to be tested using brake test rig available in Autolab. Modification mainly based on camphor and slot. Brake performance include squeal noise and squeal frequency at certain applied pressure and speed. Frequency of inter-squeal frequency from 1 kHz to 15 kHz. Partially follows squeal test procedure based on SAE standard J2521. Later I'll explain why I use partially. Reduction of squeal noise is targeted below 70 dBA. Literature review. Author Kim and Zhou. Kim and Zhou proposed 3 pad modification: the baseline model, vertical camphor, radial camphor, and inverse radial camphor. For the baseline model, there are 6 squeal frequencies. The modified pad reduces the squeal frequencies from 6 to 3 by vertical camphor and inverse radial camphor. You can see the result. Moreover, the best modification is by applying radial camphor, which can reduce 6 squeal frequencies to only 1 squeal frequencies. That's a huge difference. And Cheng Liu, he has done some simulation on pad modification. All frequencies were predicted in complex eigenvalue and numerical result. Most of the unstable mode can be reduced by applying camphor to the brake pads. Lin stated that trigonal slot is a good modification for brake pad based on prediction of disc brake squeal using complex eigenvalue analysis. The modified brake pad can reduce the squeal frequency from 9 to 1 squeal frequency. That is huge reduction of squeal frequency. Ayub modification proposal include machining 2 slot, making a V shape around the pad centerline and a diagonal camphor in both ends of the brake pad, creating modified brake pad 1. The second modification was to machine 2 slot, making U shape around the centerline of the brake pad with a radial camphor at both the brake pads and creating modified brake pad 2. 1 slot is machined in the centerline of the third set of a brake pad with a diagonal camphor creating modified brake pad 3. Result by the proposed modification shows that the noise intensity reduced by 16% with the first modification, 6% with the second modification, and huge 27% with the third modification. From here we know that third modification is the best modification. Research approach. There are several research approach: experimental approach, numerical approach, analytical approach. So I chose experimental approach because provides real data, commercial and laboratory scale of brake dynamometer, uses standard testing procedure SAE J2521, useful for validation of FE analysis, but the problem is it requires expensive hardware and software. Figure below you can see the squeal noise metrics. 3 and 10 are the speed in km per hour, 50, 75, 100, 125 are the temperature in Celsius, 0, 30, 5, 25 are pressure in bar. As I mentioned earlier, I use partially because at lowest the squeal noises are produced at lower speed
and also at lower pressure. At higher speed or higher pressure, there are only few squeal noises, and the squeal noises are below 70 dBA, which is not suitable for my case. Therefore, I use partially from the testing procedure SAE J2521. Methodology starts with squeal test for non-modified brake pad, then modification of brake pad occurs, and then squeal test for modified brake pad, data collection, data analysis, result and discussion, then conclusion. Hardware and software involved. This is the brake noise test rig, drag type. Okay, consists of manual handle, hydraulic unit max pressure 70 kg per centimeter square or 70 bar, both are similar, or 1000 psi. Speed controller shows value in frequency. So the maximum speed is 60 Hz or 1450 RPM. So I have to convert them to km per hour. Consists of electric motor, brake caliper, brake disc, propeller shaft. Maximum torque output 413 Nm, maximum speed 1760 RPM. Sensors involved. Digital tachometer measures the speed of rotating disc by shooting laser beam from the tachometer direct to the rotating shaft. I have to shoot the laser to the propeller shaft, which has a white marker for me to validate the speed of the rotating shaft. Microphone records squeal noise from brake system and locate as near as possible for the better sensitivity. Beside the picture, you can see how I place my microphone near brake system. Accelerometer record readings from the vibration of the braking system once the disc start rotating. Load cell detect the deformation at the load cell and converting them to the electrical signal to determine the force being applied to them. How I conduct my brake squeal test. First, the test. The required transducers were connected to the data acquisition system. All hardware and instrument used were set up and ensured all the equipment was in good condition. Data acquisition system was set up to record all the required parameters. Drive motor was turned on. Light reflector from the tachometer was flashed onto the rotating shaft where there is a white mark as a reference. So before I conduct my squeal test, I have to make sure all the debris from the disc are eliminated to not disturb my readings. So I have to run a bedding process. Bedding process need to be done by adjusting speed controller at 75 RPM. The rotational speed value was displayed by the speed controller and verified by tachometer. Pressure was applied manually to 10 kg per centimeter square or 10 bar and left for about 30 minutes. After 30 minutes, the brake is left cool. After it has been cooled, I can start my squeal test. Beside that, you can see data acquisition system. Duitron uses Duisoft software. Bedding in process where the brake pad changed to reddish at the surface. Reddish color at the surface. Result and discussion. Original brake pad consists of 15 tests. Table shows squeal data for the original brake pad with different rotational speed and different hydraulic pressure. Graph indicate detected squeal frequencies during the squeal event are ranged in values between 4208 Hz and 9101 Hz with maximum squeal noise of 99 dBA. So 99 dBA at test 13, 6 bar, 41 RPM, 4521 and 9053 frequency. Sound pressure level plot for non-modified brake pad. Modified brake pad 1 consists of 6 tests. Table shows squeal data for the modified brake pad 1 with different rotational speed and similar hydraulic pressure of 1 bar. Graph indicate detected squeal frequencies during the squeal event are ranged in values between 4619 Hz and 9296 Hz with maximum squeal noise of 93 dBA. 93 dBA at test 2, 1 bar, 31 RPM, 4638 and 9296 squeal frequencies. The result indicates that there is a slight reduction of squeal noise from the original brake pad by approximately 6%. Sound pressure level SPL plot for modified brake pad 1. Modified brake pad 1 has vertical slot at the middle. Modified brake pad 2 consists of 14 tests. Table shows squeal data for the modified brake pad 2 with different rotational speed and different hydraulic pressure. Graph indicate detected squeal frequencies during the squeal event are ranged in values between 5361 Hz and 9091 Hz with maximum squeal noise of 87 dBA. 87 dBA at test 9, 8 bar, 36 RPM, 5771 and 7119 frequency. The result indicates the reduction of squeal noise by approximately 12%. Sound pressure level plot for modified brightpad 2. Modified brightpad 2 has vertical slot at the middle and chamfer at both ends. Modified brightpad 3 table shows squeal data for the modified brightpad 3 with different rotational speed and different hydraulic pressure. Graph indicate detected squeal frequencies during the squeal event are ranged in values between 4121 Hz and 9140 Hz with maximum squeal noise of 80 dBA. 80 dBA at test 1, 1 bar, 21 RPM, 4570 and 9140 Hz. The result indicates the reduction of squeal noise by approximately 19%. Sound pressure level plot for modified brightpad 3. Modified brightpad 3 has diagonal slot at the middle. Modified brightpad 4 consists of 6 tests. Table shows squeal data for the modified brightpad 4 with different rotational speed and hydraulic pressure of 1 bar. Graph indicate detected squeal frequencies during the squeal event are ranged in values between 4189 Hz and 8437 Hz with maximum squeal noise at 77 dBA. 77 dBA at test 1, 1 bar, 26 RPM, 4189 and 8408 squeal frequency. The result shows huge difference. The reduction of squeal noise by approximately 22% from the original brightpad. Sound pressure level plot for modified brightpad 4. Modified brightpad 4 has diagonal slot at the middle and chamfer at both ends. So as a conclusion, 4 brightpad modifications were proposed in order to reduce squeal noise. First brightpad reduced 6% from the original brightpad with the maximum value of 93 dBA. Second brightpad reduced 12% from the original brightpad with the maximum value of 87 dBA. Third brightpad reduced 19% from the original brightpad with the maximum value of 80 dBA. And the last fourth brightpad reduced 22%, a huge reduction from the original brightpad with a maximum value of 77 dBA. Therefore, the fourth modification shows greatest reduction of noise with 22%. Although the targeted squeal noise reduction below 70 dBA is not achieved, but the modified brightpad do show some reduction in squeal intensity. It is undeniable that although much development has been carried out to solve squeal noise, it still remains unresolved issue. Recommendation for the future work: it is recommended that squeal data obtained from the test rig need to be further verified by vehicle road test, because in this experimental work the effect of environmental conditions such as wind, temperature, humidity, road debris and weather conditions are neglected. Since the proposed modification is limited to 4 type only, other structural modifications that are proven to reduce squeal noise such as radial chamfer, diagonal chamfer, horizontal slot and others can be applied. Furthermore, the modification at the disc, if there is any, should also be considered, since the friction between both the pad and disc plays a bigger role in producing squeal noise. Here's a little video for you to show how a squeal noise sounds. Quite annoying, right? These are the references I use for my project, and thank you for your time.